All right, the last model that we have to deal with here is called It's Just Math. And you'll see why that is. It's because it's just kind of an abstract problem. And there are some loosely related questions around a similar set of issues concerning that particular problem. So let's get going. Okay, so part A is simply finding the derivative of this given function, which is just this again. The function is the square root of 25 minus x squared. And the derivative of this thing is going to be the inside and then times the outside derivative. So the inside, we call that the derivative of square root of x is equal to 1 over 2 square root of x, right? This is a derivative that you could do that with the power rule, but it's also a good derivative to just memorize. That way you save a lot of time in the test. So we have 1 over 2 square root of 25 minus x squared. So the inside stays here. And then times the derivative of the outside, of the inside, that's negative 2x. So this is it. And then you can reduce it. These 2's here cancel. And you're left with negative x over square root of 25 minus x squared, like so. Okay, B is find an equation for the line tangent to the graph of f at x equals negative 3. So for that, we need to find the point on the original function at negative 3. So let's do that first. F of negative 3 is the square root of 25 minus 9, and that is 4. And then the slope that we need for the equation is at f prime at negative 3. And that is negative 3, so that's positive 3 up here. And then at the bottom, we have just the same expression as that. So that's 4. We can reuse that. So the slope is 3/4. So that makes the equation of the tangent line y minus 4 is equal to 3/4 of times x plus 3, right? Okay, that's done. Anything else on this one? No. Okay, C is a piecewise defined function, and we're supposed to find out if it's continuous. Well, when is it continuous? It is continuous if the limits of the one-sided approach to the point between the pieces, to the separation point or connection point between the pieces, is the same from both sides, right? So we have to find the limit as x approaches negative 3 from the left, and that is going to be from the left. We apply f of x to that. And that has to be, let's just see what that is, because we've already found that, right? The limit of f of x is 4. We can just use direct substitution on that one. F of negative 3 is 4, so we already know that. And then the limit as x approaches negative 3 from the right, we have to use x plus 7. And we can also use direct substitution in that one. That's negative 3 plus 7, and that is also plus 4, positive 4. So that means the overall limit of g of prime as x approaches negative 3 does exist, and it's equal to 4. And so if the overall limit exists, and the left-sided limit is the same as the right-sided limit, then that constitutes continuity. So continuity is fulfilled. And just for completion's sake, if you also want to check for differentiability, you would have to also check the derivatives as they approach -3 from the left and from the right. And if the pieces here also have the same slope as they approach -3 from either side, then the function is also differentiable. But that's not part of the question, so we're done here with this. And now we have to do d. D is finding the value of the integral from 0 to 5. That's a definite integral of x times 25 minus x squared dx. And for that, we're going to use u substitution, and we're going to put u as 25 minus x squared. So you can say let here if you want. Let u be 25 minus x squared. That gives you du as negative 2x dx, like so, right? Now, we have to replace in this original function here, we're going to end up replacing x dx. So this is by a factor of -2 too much. So we have to divide both sides by -2. And that gives us negative du over 2 is equal to x dx, right? So x dx is what we're going to replace here. And then the inside of the square root is what we're going to replace with the u. So I'm going to come back here and continue that with the u substitution. I'm going to leave the boundaries open for now. I'm just going to replace. So negative du over 2 is going to be back there. That replaces x dx. And here in the middle, I still have square root of u left over. So I'm going to fix this up by pulling -1/2 out to the front. So this is equal to -1/2 integral root u du. All right. Now, let's identify the boundaries. If I plug in the lower boundary 0, I get 25 minus 0, so that's 25. So the lower boundary is 25. And for the upper boundary, I plug in 5. That gives me 25 minus 25, and that is 0. So the upper boundary is 0. And I'll transfer this to this. Now, that's all, right? Now I just have to find the antiderivative of this thing. The antiderivative of u to the 1/2 is add 1 to the exponent. 1/2 becomes 3/2. So it's u to the 3/2, and then divide by the new exponent. So that's times 2/3. But then don't forget about the -1/2. Let me move this equal sign here a bit, so I have room for the -1/2 times, and this is the equal sign right here. Okay, and then I have to plug in 0. I have to plug in 0 and 25. So this is going to be the same as, this is 1 times 2 is 2, 2 times 3 is 6. So that's -1/6 as the factor in front. And if I plug in 0 for u, I get 0. And then minus, I already have taken care of the 1/2 and the 2/3, right? They're here out front. So I'm just focusing on u over 3/2. So this is going to be 25 to the 3/2, like so. So I can do either of these first. Seems like, let's do one side at a time here. So I'm going to eliminate the 0. And then I have negative, so that's positive. So it's 1/6. And then here, I'm just going to do the square root first. That gives me 5. And then 5 to the 3rd power is 125. So 1/6 times 125 is the actual value of the integral. Let's see if you can do anything else to this that's useful. Doesn't quite look like it. Of course, it's 125 over 6, but there's really nothing I can do other than that. Let me double check here. Yeah, I think I'm confident with these solutions. So let's double check if we get everything right. A is negative x over square root of 25 minus x squared. That's correct. Then for B, we have the prime is 3/4. I did it in reverse order here, right? Here's the prime 3/4, and f of -3 is 4. That's here, and then the equation is that. Kind of weird that they moved the 4 over to the other side without doing further resolution here, but that's what it is. So this equation is perfectly fine, though you don't have to do anything about it. And then C is the limit as x approaches -3 from the left of g of x is the same as the limit as x approaches -3 from the left of f of x, and we've already found that. So that's 4. And the limit, and then the limit as x approaches -3 from the right is using x plus 7, direct substitution. That's also 4. Therefore, the overall limit exists and is equal to 4. And g of -3 is, f of -3 is 4. So the limit of that is the same as this. So therefore, g is continuous at x equals -3. That's a little many steps here of something that is actually not quite so complicated to state. All right, now D, let u equal to 25 minus x squared. That gives you du as -2x dx. That gives the integral as -1/2 of the integral from 25 to 0 of square root of u du. That's exactly what we have right here. Then the solution is -1/2 times 2/3 of u to the 3/2 from u equals 25 to 0. That equals 125 over 3. How did they come up with that? How is it over 3 and not over 6? What did I do wrong? Oh, yeah, of course, right? Here, simple algebraic error. This 2 just cancels and makes this 1/3 and not 1/6. So there's unfortunately tiny clerical error. Does cost you points though, unfortunately. So pay very close attention to simple, stupid mistakes that can happen like this. Don't let them happen. Okay, that's it. And that is the last type of model problems. And again, in this document here, there are tons of other model problems that kind of go about it the same similar way. You see, it often has piecewise defined functions and then just kind of random stuff out of mostly differential calculus, because all the other, like many of the other models kind of emphasize integral calculus quite a bit. So I guess, that's understandable that this kind of template goes more after the differential calculus end of things.